Hello guys, so today I'm going to teach you how to do some basic constant acceleration problems using these kinematic equations that we have here on the side. Alright, so we have this first problem. An airplane accelerates down a runway at 3.20 meters per second squared for 32.8 seconds until it finally lifts off the ground. Determine the distance traveled before takeoff. So first, let's outline our givens. Actually, first, let's draw out a diagram. So we have an airplane. It's going down a runway with an acceleration of 3.20 meters per second squared until it finally lifts off the ground. We're also given t equals 32.8 seconds. Alright. We can assume here that the initial velocity v0 is 0 meters per second. Because in the problem, it says that it accelerates down a runway, and at airports or when airplanes lift off, they start from rest, obviously. So we can assume that there, and we're looking for the distance traveled. So we have acceleration, we have time, initial velocity, and we're looking for distance or change in x. So we have change in x equals question mark. Alright, so then we're going to take a look at our equations. So we need an equation that incorporates the acceleration, the time, the initial velocity, and the change in distance. So number one, boom. Okay, so number one doesn't have the change in x, so we can't use that. Number two uses the velocity right here, which is not given to us in the problem. We only have the initial velocity, so we can't use that one. It looks like number three works, and number four uses this velocity. So we'll start out with this kinematics equation. So change in x equals initial velocity times time plus 1/2 at squared. Change in x is what we're looking for, and we know this here is going to be 0 because initial velocity is 0, plus 1/2 times 3.2, which is our acceleration, times our time, 32.8 squared. Now plugging this all into our calculator, we can find that the answer is 1,720 meters. And again, we want to leave this in 3 sig figs, because any more than that could be inaccurate, and that is typical convention. Alright, now moving on to number 2. A car starts from rest and accelerates uniformly over a time of 5.21 seconds for a distance of 110 meters. So we have a car accelerating, and it starts at rest. So it starts at rest, accelerates. We know that it is undergoing acceleration. We know that it's a time of 5.21 seconds, and the distance is 110 meters. So organizing our givens here, we have v0 equals 0 meters per second. We have time equals 5.21 seconds. And we have change in x equals 110 meters. And we're looking for the acceleration, so that is what we are solving for. Alright, so we have 3 givens and 1 unknown, so that means that we can choose one of our kinematics equations. So let's see. Again, the velocity is not one of our givens or one of our unknowns that we're solving for, so that means we're going to use the same equation as last time, number 3. Change in x equals v0 times time plus 1/2 at squared. Alright, now we can plug in our values. 110 equals, this part's going to be 0 again because the initial velocity is 0, plus 1/2 times a times t squared. Now plugging this into our calculator, we can find that the acceleration value is about 8.1 Alright, so plugging this into a calculator, we find that the answer is going to round to 8.10 meters per second squared. And then we keep this answer in 3 sig figs again. Alright, moving on to number 3. So Upton Chuck is riding the giant drop at Great America. If Upton free falls for 2.6 seconds, what will be his final velocity and how far will he fall? Alright, so with this question, we are given that he free falls for 2.1 seconds. We're looking for his final velocity and how far he will fall. And also, so this part where he free falls gives us 2 useful pieces of information. So from this, we can assume not only that v0 is equal to 0 meters per second, we can also assume that the acceleration is going to be due to gravity. So that will be negative 9.8 meters per second squared. And then we're given the time, t equals 2.60 seconds. So we're looking for his final velocity, and we are looking for the distance he will fall. Again, this change in x value, this can be replaced to change in y if that's easier, since we're dealing with free falling, which is like the y axis. So let's go ahead and change this to change in y equals question mark, just so we kind of differentiate between our x values and our y values with the acceleration, the velocity, and time. Okay, so it doesn't really matter which one you solve first. Since it asks for velocity first, let's go ahead and solve for velocity first. So we can use our first kinematics equation right here. V equals V0 plus AT. Substituting in, we can get V equals 0 plus negative 9.8 times 2.60. And then this gives us a final velocity value of negative 25.5 meters per second. Now we can solve for how far he will fall, or the distance that he falls. And let's go ahead and use our same variables that we're given in the problem, just in case if we get this one wrong, which we didn't, but if this were on a test, if we got the final velocity wrong, we could still get the change in direction, the distance that he fell correct by using the given numbers. So let's go ahead and use our third equation again for this part of the problem. So we have change in y equals v0 times time plus 1/2 AT squared. Plugging in our values, we can get change in y equals 0 due to this initial velocity being 0, plus 1/2 a, which is negative 9.8, times t squared, which is 2.60 squared. Now, plugging into our calculator, we can find that the answer to this will be negative 33.1 meters. It's also important that you make sure that your units are consistent throughout. So if it gives you this 2.60 seconds and it asks you to find the velocity in meters per hour, then you should make sure to convert the seconds to hours to keep your units consistent throughout the problem. Alright, let's move along to number 4 here. A race car accelerates uniformly from 18.5 meters per second to 46.1 meters per second in 2.47 seconds. Determine the acceleration of the car and the distance traveled. Alright, so we are given here his initial velocity, final velocity, and time, all in this first sentence here. So V0 equals 18.5 meters per second. His final velocity equals 46.1 meters per second. And the time equals 2.47 seconds. So we are looking for the acceleration and the distance traveled. We can go back to x here because it's not moving in a vertical direction, it's moving in a horizontal direction. Alright, so for solving for acceleration, we can use our first equation again. V equals V0 plus AT. So solving for this, we can get 46.1 equals 18.5 plus 2.47a. So then we can manipulate this equation to solve for acceleration. So we get 27.6 equals 2.47 times the acceleration. And we get an acceleration value of 11.2 meters per second squared. Alright, let's move a little bit to the right here. Okay, now for solving for the distance traveled, we're going to want to use the givens that we have again. So we're going to find an equation that does not incorporate the acceleration into it. And so we can find that that will be equation number 2. So we can find that that will be equation number 2. So we have the change in x equals final velocity plus initial velocity divided by 2 multiplied by t. So now we can substitute in our values. 18.5 plus 46.1. The order of this doesn't matter because it's addition. Multiplied by 2.47. So now it's just a matter of plugging into your calculator. So this will be change in x equals 32.3 times 2.47. And we can find that the change in x value, the distance traveled, is going to equal 79.8 meters. Alright, now we can move on to number 5 here. A feather is dropped on the moon from a height of 1.4 meters. The acceleration of gravity on the moon is 1.67 meters squared. Determine the time for the feather to fall to the surface of the moon. So, we are given that the feather is dropped, implying that the initial velocity is 0. We are given the distance traveled in the vertical direction, 1.4 meters, and we're given the acceleration due to gravity on the moon. So we can write out our givens here. V initial equals 0 meters per second. Our height, change in y, is going to be negative 1.40 meters. So this value is going to be negative because it's dropping from a height of 1.4 meters because the feather is dropping from a height of 1.40 meters to a height of 0 meters. So that change is going to be a negative value. And so our acceleration is going to be 1.67 meters per second squared. However, since the feather is dropping from a height of 1.4 meters to the surface, it's going to be falling, so it's going to be moving in the negative direction. So it's also going to be accelerating in the negative direction. So we're going to want a negative sign here. And then our time is what we were solving for. So that'll be a question mark. So looking through our equations, we will use equation number 3 because we're not solving for velocity and it's not given in the problem. So number 3 is the only equation that does not incorporate the final velocity as its variables. So plugging this in, so writing out our equation first, we're going to have change in y equals initial velocity times time plus 1/2 acceleration times time squared. Now we can plug in our values. Negative 1.40 equals 0 plus 1/2 negative 1.67 times t squared. So negative 1.40 equals 0.835 negative 0.835 times t squared. T squared equals 1.6766. You want to remain at least around 5 sig figs until your final answer, which is where you're gonna go back to 3 sig figs, which is what we're given in the problem. 3 sig figs in. So we're giving the distance in 3 sig figs, and we're giving the acceleration in 3 sig figs. So now we simply square this number, or we square root this number, and we find that our time is 1.29 seconds for the feather to drop to the surface of the moon. Alright guys, thanks for watching this video. I hope you learned a little bit about doing problems related to constant acceleration, and hopefully you can use this abilities in your Physics 1 classes or IB Physics 1 classes, and so you can perform well in the future.